Good morning, everyone, and thank you to David and Lucas for giving me the opportunity to share some of my research with you today. My name is Karen McKinnon. I'm an assistant professor at UCLA in the Department of Statistics and the Institute of the Environment and Sustainability, and today I'll be talking to you about some of my work on continental heat extremes and climate change. So we know that one of the clearest signals of climate change is an increase in global temperature. This time series from the Met Office just shows estimates of the global mean temperature using different data sets from 1850 to present. And what we can clearly see is that there has been a rapid uptick in global temperature, largely due to human influence. In addition to this increase in global temperature, we expect land to warm more than ocean, so land will warm more than the global mean, due to, in the transient sense, both its lower effective heat capacity and approaching equilibrium, its higher aridity or lower water content. But the question that we want to think about today is, what do these large-scale, relatively well-understood changes imply about changes in extreme heat? And it turns out the answer to that depends on both the underlying distribution of temperature. I'll be thinking about daily temperature here due to the importance of those timescales for extremes, and how that distribution is changing. So just to show the importance of those two factors, I have here just this classic IPCC figure from 2012, looking at how different changes in temperature distributions map onto changes in extremes. So in the top, we have a simple case where we imagine the temperature just normally distributed, and we shift the mean for a normal distribution. That just describes a full shift of the distribution towards warmer temperatures, and that leads to, of course, fewer cold extremes and more warm extremes. In the middle here, we have a case where we again begin with a normal distribution and we have increased variability, so the mean here does not change, but the tails both change, and so even without a change in the mean, we see increases in warm and cold extremes. And then this last case is in some sense more relevant for the real world. This is a case where we actually do start with a normal distribution in gray, but then the symmetry changes. So we end up with a non-normal distribution. And then in this particular case, that leads to actually no changes in cold extremes, but an increase in warm extremes for this particular change in the symmetry. And here we're really going to ask a question somewhat motivated by these graphs, which is, are changes in hot extremes amplified compared to changes in the mean? In other words, we expect to see changes in mean temperature, but how do changes in extremes look compared to those changes in the mean? But importantly, we cannot just think about the variance or the variability of a normal distribution, because it turns out that daily temperature almost anywhere around the world is distributed non-normally. So we need to kind of move beyond these schematics with normal distributions and think about ways to estimate changes in non-normal distributions. So just to show you what that looks like, this is just one example of a probability density function of daily summer temperatures in my hometown of Boulder, Colorado. We're looking here at the distribution of daily maximum temperature anomalies. The center of that is around 30 degrees Celsius in non-anomaly units. And what we can see here in Boulder is that this distribution is so-called negatively skewed, meaning that there's an asymmetry where you are more likely to have, say, a temperature anomaly of minus 10 degrees Celsius compared to, say, one of 10 degrees Celsius in the positive side, which almost never happens. And it turns out that this non-Gaussian behavior, and even particularly this negatively skewed behavior, is quite common around the world. So what I have shown here are some maps. Each point on this map is a weather station that has high-quality data within the Global Historical Climatology Network database. And this is really a major database that we have for ground-based in situ measurements around the world of weather and then climate. Before I actually talk about what these graphs show, I always like to have people think for a moment about the spatial distribution of these stations. And so if we think about really wanting to understand climate change around the world, and in particular in places that might be more adversely affected by climate changes, it's pretty notable that there's few publicly available high-quality measurements of things as basic as temperature across, say, much of the continent of South America and Africa and other places around the world. That's not to say these data don't exist, but rather that they're not available in these global public databases. And so to really do high quality studies in some regions around the world, there's a need to really get more local, perhaps proprietary data sources. But what's on these maps? This top map is just showing skewness. That's what I was emphasizing in the previous plot. It's the third moment of the distribution. It is 0 if you have a normal distribution, non-zero if your distribution is non-normal. And what we can see is around the world, daily temperature over land during the summer tends to be negatively skewed, except on the western coasts of continents where you have a large maritime influence. This lower plot is so-called excess kurtosis. This is basically how much extra weight there are in the tails of a distribution. It's not super important what these numbers mean, but the point is simply that any of these stations that are not gray also show significant excess kurtosis. And so what we see from these two maps is that we don't really want to begin with the assumption that temperatures are normally distributed on the daily timescale. Because they tend to not be at most locations around the world. And therefore, when we assess changes in the tails of a distribution, we need to kind of move beyond just thinking about changes in the mean and changes in the variance. So there's a few ways to do that, but the one way that I'm going to explore here is a method called quantile regression. Quantile regression at the end of the day is relatively simple. If you think about your normal ordinary least squares regression as estimating the change in the mean of a distribution, quantile regression simply generalizes that to estimate changes, in this case in time, in other percentiles of a distribution. So I'm demonstrating that here with summer temperature data in Roosevelt, Arizona, just a randomly chosen example. Each one of these dots is a daily temperature measurement from 1980 to 2015, which will be the period I'll focus on this first half of the talk. And the trends are shown here of the 5th, 50th, and 95th percentile of those temperatures as a linear function of time. Now in this plot, I want to use it more for a demonstration than to make any particular quantitative conclusions. It's up simply to say here that you can imagine that in this case, say the 95th percentile of temperature is actually increasing at a greater rate than the 50th percentile of temperature. And so if we were to kind of go into this further, maybe assess the significance, if there's a difference between those two, this plot might be suggesting that these hot extremes are actually increasing at a rate faster than the middle of the distribution. So what I'm going to do is do this type of analysis for stations throughout kind of North America, the United States, and Eurasia, looking mostly at the linear trends in the 50th and the 95th percentiles of these daily temperatures during summer. And that's shown here. And the top here we have those linear trends in degrees Celsius per decade of the 95th percentile, on the bottom in the 50th percentile of temperature. Now I'll first point out that in the United States uniquely, we actually do see cooling across much of the country over this time period. I collaborated on some work led by Nathan Mueller that pretty convincingly argues that the cooling in the Midwest is related to how much corn we plant in that region and the large amount of evapotranspiration that goes on related to the corn. And then there's been a lot of discussion that I've been less involved with about the kind of warming hole in the southeastern United States. So these cooling trends are actually real. They are not likely an artifact of the data. But then if we look at the places that are warming, we can compare the trends in the 50th percentile to the trends in the 95th just visually here. And we see that actually the trends in the 50th tend to be somewhat greater than the 95th, so we don't see an amplification of these heat extremes with respect to the median. We see that perhaps there's even some damping. Now in order to summarize that, I'm going to describe changes in these summer temperature distributions in this plot just with two metrics, although in the paper we actually look at a total of 4 metrics, but these two explain most of the picture. And these two metrics, this first one I'm calling the shift, and this is just the trend that is consistent across all percentiles of temperature in the distribution. So although I've only shown you the 50th and the 95th here, we actually examine trends across all percentiles in the distribution from the 5th to the 95th. And the shift behavior just says, how are all of those percentiles changing? And so we can think of this as basically, even for a non-normal distribution, just doing a rigid shift in all those percentiles towards warmer temperatures. And what we can see is that same west-east pattern that we saw in the previous plot, where the west is really warming in all percentiles and the east tends to be actually cooling across all percentiles. Then on top of that, I have the second way to describe the data, which I'm going to call the stretch. A positive stretch just means that you're having greater warming in your higher percentiles, those hot days, and less warming in your cooler percentiles, those cool days. And the negative, of course, would be the opposite. So what we see here is that in one part of the United States, kind of eastern Texas, we see positive stretching where you do have enhanced warming at those extremes. But in much of the rest of the US, that metric is actually negative. And so we're seeing kind of an increase overall in the whole distribution in terms of this shift, but some shape changes leading to a contraction of the distribution so that we don't see an amplification of hot extremes compared to changes in the mean. Now we're going to hop over to Eurasia and look at what we see there. In this case, in general, things are just warming more overall. And based on this plot, we might also suggest that there is greater warming in the 95th percentile compared to the 50th. And indeed, if we again divide this data into this shift behavior where all percentiles are just warming the same amount versus this stretch behavior where you see in the positive sense a greater warming at those high extremes, we do indeed see that across a large swath of Eurasia there does appear to be some stretching of the distribution that's going to be amplifying those hot extremes. So then we can kind of pop back to the IPCC figure and just update it, not that it was incorrect in any way, but just give kind of a revised version based on observed changes in temperature distributions in different places around the globe. So in the western US, I talked about that first, we essentially see a positive shift of the distribution going from that gray line or the gray histogram to the black histogram, but actually a negative stretch. So the distribution is contracting somewhat, and that means that our hot extremes are not amplifying as much as they would if we didn't have that negative stretch. Now in Eastern Europe, we're seeing a pretty large positive shift and a pretty substantial stretch, and that means that hot extremes in Eastern Europe are being amplified substantially compared to what they were a couple of decades ago. And I didn't talk about this third case too much, but beyond the shift in the stretch behavior, you can look at more complex changes in the shape of the distribution. And in the northeastern US, looking actually at daily minimum temperature, you actually see very little change in either the mean or the hot extremes, but there is some change in that lower tail where you see a decrease in cold extremes compared to what they used to be. And so in some kind of small regions around the world, other types of more complex behavior are dominant. What I've talked about so far is just based on the observations from a relatively short period, 1980 to 2015. And a question that we always have to ask when we analyze the observations is, are these changes so-called forced, and meaning are they a response to human influence and therefore we might expect them to continue into the future, or are they to some extent a sampling of just internal variability? So I don't have time to go into the details here, but this plot is based on the so-called NCAR-CESM1 large ensemble. And what these large ensembles are, these initial condition large ensembles, is a set of model simulations based on the same model, the same set of radiative forcing, but where each member of the ensemble has a slightly different set of initial conditions, basically machine precision, noise, and atmospheric temperatures in this case at the beginning of the simulations. And what we can do with these ensembles is average over all of the members and get some at least model-based estimate of the true forced response to climate change. And so I've done that with 1980 to 2015 data in this model set. And what we see is that shift behavior, where essentially all percentiles of the distribution are changing in tandem, so the 50th percentile and the 95th kind of move in lockstep, is pretty dominant around the northern hemisphere, whereas the stretching behavior that we saw evident in a couple of regions is, it's not non-zero, and it explains some of the structure that we see in the model, but it's a relatively small contribution. And then interestingly, we can also think about, do these trends in the model look like what we've seen in the observations? And I don't have time to go into all of the details here, but it's interesting to note that kind of that hot spot of warming in Eastern Europe, north of the Black Sea, is evident in the ensemble mean of the large ensemble, as well as here in our estimates from the observations. But there are other cases where there are clearly differences. Okay, so in my last few minutes, I just want to talk also about heat extremes and their connection to humidity. So many of us know, either scientifically or from our own personal experience, that the impact of heat really depends also on humidity. So there's this thing called the heat index that you might see on the news. That's just how hot will it feel on a given day. And hot temperatures tend to feel more hot if it is more humid, because our body is less efficient at cooling through evaporation. Conversely, crop yields tend to be adversely affected by hot, dry temperatures, and of course the spread of wildfire is also increased, or the risk of wildfire spread is increased during hot, dry days. And so when we think about heat extremes, I think increasingly want to think about how those are connected to other components such as humidity. And so here I'm just going to briefly present some analyses that are looking at how humidity is changing on hot days. Now, answering that question is a little bit less straightforward than what we just did with temperature because heat and humidity are not independent of each other. So this plot shows at a number of weather stations around the world in the Global Summary of the Day database the correlation between temperature and specific humidity. And what you can see is that in most places around the world, the two are positively correlated, such that hotter days tend to be more humid. But in some cases, such as more arid locations or places influenced by the monsoon, there is a negative correlation. But regardless, we can see that there is, of course, a non-zero relationship. So when we think about changes in humidity on hot days, we essentially need to model that relationship between temperature and humidity and then understand how it is changing. So I'll just show one example here. This is data from Mason City, Iowa, looking at July, August, September temperature and humidity from 1973 to 2019. In this plot, what I have shown is a 2D histogram of all of that data over the period. And temperature anomalies are on the x-axis here, and specific humidity anomalies are on the y-axis, although I'm missing my label. And what's shown with these black lines is, again, a quantile regression-based analysis, but here we're looking at the fit of the 5th, 50th, and 95th percentile of specific humidity as a function of temperature. And so what we can see is that this model can essentially capture some of the nonlinear and kind of complex behavior between temperature and humidity. But what we want to do with this model is actually estimate how these relationships are changing over time with increasing global mean temperatures. So what I've added here is on the left, here is data from the first half of this record, and those same spline fits, but conditioning on essentially lower than average global mean temperatures. And on the right here, I have similarly the data from the second half of the record and those same spline fits in black, conditioning on higher global mean temperatures. And the gray lines in this right plot are reproduced from the black lines in the left plot, and they're just showing, therefore, the spline fit at the beginning of the record. So if we take a look at this red line, this is just showing the 95th percentile of temperature. We can see that essentially humidity on these hotter days is increasing across all percentiles of humidity, much more than it is on, say, an average temperature day or a colder than average temperature day. So these increases in humidity are amplified at high temperatures. And if we had not done this kind of fit as a function of temperature, we would probably miss that, or we definitely would miss that if we were just looking at changes in humidity independent of temperature. So I'm now going to zoom in. It's probably a little bit hard to see depending on the size of your screen, but just on a single metric, which is the change in the 95th percentile of specific humidity on hot days over the period of record. So basically the move from this gray line to the black line for the 95th percentile of specific humidity on those hot days. And I'm showing that number here just as a plot across the United States. And there's a lot in this plot, and this is new work that I still need to spend some time analyzing. But I'll just point out here one example, which is that across the Midwest that I've outlined in black, we can see that those hot, humid days are getting more humid in a pretty substantial way. So this is maybe, say, 2 grams per kilogram increase in specific humidity on those days that are already hot and humid. And we can look at how those humidity changes for those on the 95th percentile of humidity are changing as a function of temperature percentile. The 0 line here is in blue, so we can see that essentially in the Midwest, essentially independent of temperature, we're generally seeing increases in humidity, but again that those increases are amplified on those hot days. And so if we had just looked at changes in high humidity days independent of temperature, we would miss that amplification that we see on hot days. So I have 45 seconds left here, so I'll just briefly sum up what we found, which is that we can look at changes in temperature distribution using quantile regression and understand both how the whole distribution is changing and how its shape is changing as well, which is important for extremes. And then similarly presented some new work using a somewhat more complicated quantile regression model that enables us to look at how humidity is changing as a function of temperature and over time. And just point out one example that in the Midwest we see an increase in humidity on those hot, humid days, and that magnitude increases with temperature. So I think there's still a lot to learn about heat extremes. We of course know that temperature is going to increase over time as we continue to affect our global climate, but there's a lot of things that we can still learn about heat extremes, such as if we can improve our predictions of them in order to reduce their impacts, understand the relative roles of the land and the atmosphere in causing these heat extremes, using that understanding to reduce the biases in climate models. And then there's a lot to learn about these compound-related heat extremes, how to model them, and how are they changing. So thank you very much, and I look forward to the discussion at the end of the talks.